So while doing my research for this interview, I came across a staggering statistic about the number of people suffering from one form of paralysis or the other in the United States, right? So some one in, I guess, 50 people in this country suffer from some debilitating inhibitions to their lower and or upper extremities, right? So that's over 5 million Americans. So this is a pressing problem. I feel it doesn't get the notoriety it deserves, right? So to add to this, there's this common stigma that comes with being paralyzed, right? This feeling that you're always going to be a burden to other people, be it your family or your friends. And another stat that took me aback was the fact that only 15% of individuals living with paralysis are actually employed. Now, this is financially and
Wow.
ontologically concerning, if you ask me, because as human beings, right, we derive so much meaning from our work. Now, I guess I can't stress enough why the work of today's guest is so prescient, right? So today I'm talking to Dr. Norman Sumner, right? So Norman is a Della Martin postdoctoral fellow in the Division of Biology and Biological Engineering at Caltech. Now, on his website, he states his research goal is to give back motion to those who have lost it, right? Now, that's a noble goal if I've ever heard one. So welcome, Dr. Norman.
Yeah, thank you so much. I'm totally shocked by the second statistic. I've thought a lot about how many people have paralysis. I
Mm,
never heard that 15% of them were working. That's
okay.
wow. Yeah.
Yeah, that's good to hear because I'm sure I'm gonna learn a lot from you, and I feel warm inside knowing that you've actually already learned something from me
Yeah,
already.
this is great.
All right. So now, staying true to tradition, I always have my guests give us a walkthrough, of their journey through, science. So in your case, it's not going to be any different. So I want to hear how you've been able to peruse, this thing we call academia and how it's gotten you to where you are to today.
Sure, yeah. I come from a fairly unlikely background. I grew up in a small town in Utah. I think it was about 5,000 people when I was a kid. Didn't know any scientists, never met any scientist or engineer until I was a bit older in life. On a trip with my parents when I think I was about 10 or 11 years old, we went to the Boeing factory, and I got to meet one of these engineers, and I saw side by side, this is back in the 90s, so a CAD drawing, computer aided drafting, green lines on a black screen, he was drawing something, and then sat the part on his desk. And I remember thinking, like, that's the guy. He's the one that thinks of something and then it becomes real. And so from there, I decided to follow a career in mechanical engineering. I wanted to be like him. So went to college at the University of Utah, where I studied mechanical engineering. Quickly found a passion for research when I applied for a summer research program at Brigham Young University, where I did solid state theoretical physics, X-ray crystallography. That's really where I learned to program properly. There was a lot of computation. Uh, that and growing on that, as far as research goes, I just immediately started looking for more opportunities. In the fields of mechanical engineering, a lot of the kind of planes, trains, and automobiles, the things that I went into it for, there was probably less research opportunity at that time for me than there was for robotics. And I really, really loved robotics and control theory. So my first lab was a haptics and embedded mechatronics laboratory at the University of Utah as an undergraduate, where I worked on devices that basically guided people around through the sense of touch. And we were really interested in the science of touch and how we perceive touch in kind of a human computer interface sense. When someone mentioned to me, hey, that device would be really useful for someone who's had a stroke or other types of paralysis that needs to do some type of like tabletop therapy at home, where you can sort of automate what normally people would be doing with a therapist. And I thought, well, that's kind of interesting. And so my first real academic publication was centered around how devices like these could potentially be used for stroke rehabilitation. And then it really started tumbling, because when I applied for my PhD, I visited the lab of David Rankensmeyer, who eventually became my PhD advisor. And he's kind of one of these just amazing human beings who cares so much about fixing a problem. And I felt his passion for trying to restore movement to people. and really thought that that's where I could make a difference. And he has a long history of developing exoskeleton robotics for stroke rehab and spinal cord injury rehab, so both upper and lower extremity. I started developing robotics during my PhD to that end, especially interested in finger and hand fine motor skill development after stroke, and eventually found that the cases where people were most paralyzed, they needed the most help, these are the ones that we had the hardest time helping, because how does a robot amplify a force if the person can't produce a force at all or produces the wrong forces? And so the way that we looked at this problem was, instead of looking to the peripheral nervous system, the hands, why don't we look back to its origin at the brain? And if we can read signals directly out of the brain, and these signals we know to be conducive to good therapy versus less good therapy, how can we encourage good brain states that create good movements, and then we can repeat that many, many times with an automated robotic environment. And so that's how I got into brain-computer interface.
Wow, thank you. That's a very in-depth and succinct explanation of how you've done this thing called research. So I know we're going to talk a lot about brain-computer interfaces, right? So, or people call them brain-machine interfaces, right? So what are these on a fundamental level? And are there any that are ubiquitously in use today that my listeners might actually kind of recognize? Oh, I know that. So that's what it's called.
Yeah. So brain-computer interface, brain-machine interface are the same thing. They're used interchangeably in the field. We can't seem to decide which one to use. There are some of these in use today. There are deep brain stimulators that can limit tremor. There are, oh geez, I'm gonna forget the name of it now. The stimulation protocols that you can put into the ear that allow you to hear.
Is
Just
it cortical, something like that? No?
no,
Or I'm thinking of something else.
I'm sorry. Let me look it up really quickly.
Sure, no problem. Yeah.
I
I
hope you
know
don't
that
mind
feel.
if I do.
No, that hey, it's a long discussion, all right? So we've got time.
I can't believe that it just like escaped my head. Oh my gosh, now I can't even look it up properly.
Uh,
And it's like it is the number one thing, oh
all right.
jeez. Cochlear implant. Okay.
Yeah, yeah, I was
Yeah.
gonna,
Okay.
yeah, yeah.
Sorry.
No problem.
Yeah.
Yeah.
So there are a
Hmm.
number of BCIs or BMIs that are available to people these days.
Hmm.
And the number one, the most common one, is a cochlear implant. So
Hmm.
this is something that's going to allow a person who was formerly deaf to actually hear again, which is pretty incredible. And we tend to almost forget about just how amazing these things are because they integrate so seamlessly into some people's lives. Similarly, we have deep brain stimulation for people that have essential tremor or Parkinson's. And these are really just kind of the first steps into brain-machine interface. As I mentioned, both of these are stimulation. So they actually put electrical impulses into the nervous system to create a percept or to change the maladaptive brain function that might be happening due to the injury or disease. But what we are really interested in is bidirectional. Ultimately, in the future, we want to be able to read information out of the brain to interpret what the brain's intentions are, as well as stimulate the brain to create some percept or change some behavior of the brain. And together, this is a bidirectional BCI. So that's where the future is really headed.
Interesting, interesting. So it seems like BMI. So BMIs again, for those who are not initiated, brain machine interfaces, right? So we're going to be calling it BMI the whole time, right?
Yeah.
Because it's kind of a mouthful. So they've come a long way, I assume, right? So from the time they were starting to truly get academically studied by researchers like Professor Jackie Vidal at UCLA, to the truly groundbreaking work that people like yourself are doing. So how would you assess the current state of BMIs, right? So is the progress, I guess, commensurate with the pressing need for these devices, would you say?
I don't know if I would say it's commensurate. It's definitely picking up.
Mhm.
It is just so incredible to see how the acceleration has changed from the time that I entered the field, which was not that long ago, right? You know, you're talking less than 10 years. I've been researching this. And in that time, I have seen the amount of investment both in public, private industry, and academia, especially, just skyrocket, which is wonderful. The progress that's being made in comparison, where you've had 100 years of EEG recordings, and like you mentioned, 30, 40 years of EEG for brain-machine interfaces. Now, within just a 10-year span, we're seeing, double, triple, quadruple progress because of an influx of new recording technologies to get information out of the brain. Massive user adoption, both at the user level and at the kind of level of the laboratories. But as you mentioned, the problem is so big that I would never say that we're there yet. Until it's solved, like, I think the pace just has to keep increasing.
Interesting. So what you're saying is certain technologies are starting to kind of intersect with the need for researchers in BMIs, right? So we're seeing some sort of pickup in the pace of creating these devices that are actually in need by these people with these debilitating conditions, right?
Yeah, that's right. Unfortunately, although there's been a big pickup in research, most of that research is still years away from actually being available to a consumer or a patient.
Mm.
So the devices I mentioned earlier, cochlear implants and deep brain stimulation, have also been around quite a while. And they've improved somewhat, but they're still in their kind of core form. They haven't changed a whole lot. Now, what's kind of coming in the pipeline is revolutionary. You're starting to see really big jumps in the field. And it's clear that there's a proof of concept for many different types of BCIs and the way that they can affect people's lives. But I think we're still probably years away from seeing a lot of those actually in people's homes.
Interesting, interesting. So this brings us to your work, right? So the truly effective BMIs today are based on intracortical electrophysiology, right? So we're really permeating brain tissue to access neuronal electrical activity, right? So this is, I guess, as grimy as it sounds. So we're gonna talk highly we're going to talk about highly invasive surgery, right? So, can you explain to us how it's currently done? And I say, don't spare us the gruesome details on this, and how your team is, what approach your team is taking with your functional ultrasound technology.
Right. Yeah, so not all BCIs are invasive. There are non-invasive ones, and those include EEG or functional near infrared spectroscopy, et cetera, et cetera. But the most high performance BCIs, the ones that we tend to learn the most about the brain from, are invasive. And right now, the only FDA approved device for human chronic use is the Utah array. The Utah array looks like a tiny, tiny bed of spikes. You can fit the entire bed of about 100 of these little spikes on the head of Abe Lincoln on a penny. And then you take this device, you have to cut a small hole in the skull, remove the skull, and then actually cut open the dura mater, which is the protective membrane that surrounds the brain, peel that back. Then you basically set the device on the surface of the brain, and using a pneumatic gun, essentially, you shoot this thing down into the cortex. And so the spikes all penetrate, and then kind of when the bed hits the top of the cortex, that's where it stops. And
Oh my
then
God, are we talking about some medieval torture device right now?
it sounds pretty scary. Luckily, you're asleep for the whole thing, so but
Yeah.
the recovery is definitely not trivial, and it is not for the faint of heart. I cannot emphasize enough how inspiring these patients are that go through this.
Wow.
These are people who are typically tetraplegic, so they haven't moved in potentially decades.
Mm.
And that's a huge amount of burden on themselves and their family, and yet they choose to add all of the surgery and recovery because they want to help science progress, and they understand their critical role to do that. It's really pretty amazing to meet these people that are willing to undergo these types of surgeries. And remember, these devices only last 5, exactly how long it varies person to person. So far, we've been lucky. 5 and 6 years is quite common. But at some point, you will either have to be reimplanted, which means a second surgery, and then eventually at some point, you will be explanted to take the device out. So it is not just one surgery, but multiple.
Wow, wow. So yeah, I guess I did interrupt you at the point where you're saying we take out a chunk of the skull, then we put this device in, right? Sorry to mess up your flow. What else
Oh
do you
no,
have
that's
for us
totally
on that?
fine.
Right.
Yeah, and the other thing is,
Mhm.
these devices right now, the way they work is we implant the device itself into the brain, but a cable actually has to come out, and a pedestal is actually screwed into the skull from the outside. So these people have what, in a kind of very matrix-like way, a small plug that sits in their head. So when they come to work with us, we literally plug them in with a cable.
Wow, wow. Okay. Well, okay, that got me sweating a bit. So, all right, it seems to me there's, I guess, a whole host of issues with intracortical electrophysiology, right? So, the brain tissue might be damaged during these procedures, right? And the fact that we're putting electrodes into brain matter, there might be degradation over time. So, what other technical issues are, I guess, present with the current state of this technology, would you say?
Yeah, so longevity, you kind of hit on there. They don't last forever. Eventually, they are encapsulated by glial scarring, so that the brain essentially encapsulates these electrodes. So our recordings slowly decline in quality over a period of years. So that's one issue. The other issue is that they are not, you can't span these things over the entire brain, because as you mentioned, they do actually create small amounts of damage as they go in. So for someone who's tetraplegic and unable to move from the neck down, their motor cortex is not necessarily innervated in the brain the same, or innervated into their bodies the same way that you and I are. So to them, it is a worthwhile trade-off to some degree if you lose a little bit of, if you have a small amount of damage, but it gives you the ability to move a robotic arm or a cursor on the screen. That trade-off makes a little bit of sense. But for someone who still has decent function, say someone with moderate or mild paralysis after a stroke, you don't want to damage any of their cortex. They already have some damaged cortex in many cases and are trying to recover from that. So you really want a device that isn't going to cause any harm or as very little harm as possible, and hopefully is scalable in a way that you can look at larger areas in the brain, because the Utah array is, just a couple millimeters wide. You're not going to be able to decode many, many types of signals from the brain, because different areas of the brain have different jobs. And there's that gets a little bit complicated in how they mix their encodings, but um, roughly speaking, more brain is better.
All right. So that's interesting. So this actually brings us to the work that you're doing, right? So according to your paper that I read, functional ultrasound, right, is I guess something called hemodynamic technique that maps out regional blood flow. So kind of like the Doppler effect with sound and light, right? So can you talk about your work and this device that you guys are actually working on in your lab?
Yeah, sure. So the Doppler effect everyone is familiar with. When an
Yeah.
ambulance drives
Drives
by,
by, yes.
it's a much
Mhm.
higher pitch as it approaches and then becomes low as it goes away.
Mhm.
And that's the sound wave sort of compressing with the speed of the ambulance as it comes, and then decompressing as it goes away. And the same thing happens in the brain when we use ultrasound. So as we transmit waves of mechanical energy, so small ripples at the frequency above which we can hear, meaning ultrasound, these ripples go down and they echo off tissue interfaces. As they do that, they will also echo off things that move, things like red blood cells. So as red blood cells travel towards the ultrasound transducer, they tend to slightly increase the pitch at which what we hear echoing back is actually received. As they go away, we see a shift down in the frequency. So that is the Doppler effect, just like the ambulance. So we listen for kind of changes in the pitch of the red blood cells, if you will. We don't literally listen, of course. We use, an ultrasound array that goes to a big acquisition machine, and then we compute where the blood flow changes are. And then the real trick was the advent of ultra-fast ultrasound, which was about 10 years ago. It was pioneered by our collaborators in Paris, Mikhail lab, who are just an incredible team.
What school
They
are they out of? What school
they're
did
out
they?
of INSERM actually,
Oh,
and then they also have a company that they're spinning off now as well, Iconius, and so it's definitely a growing area. Uh, but the basic idea is that traditional ultrasound, if you get a sonogram like a wound, for example, most people are familiar with, that scans line by line. So every line in the image has to be reconstructed one at a time using a focused beam. And so you get about 50 images per second. Our collaborators came up with a way of energizing the entire ultrasound array at once. So you create a plane wave, and that plane wave emanates through the tissue and echoes back. And with one shot, you get one image. And that means that you can image very, very fast. And we're talking tens of thousands of times per second, rather than the kind of usual 50 to 60 you get with conventional ultrasound. That affords us a lot of new ways of using the data. So we steer the beam at slightly different angles. That increases our resolution. We repeat the numbers and average multiple frames together. So that increases our sensitivity. And then once we do that, we can actually look at big compound gaps of these images or many frames all at once to look at what's moving in the image, what's creating this Doppler effect. And if we filter it just right, we can see what is the brain tissue moving, what's kind of heartbeat, but also what is very localized blood flow, what areas in the brain, even down to like 100 micron or smaller. So these are, roughly the width of a human hair. What areas in these little tiny capillary beds and arterioles are seeing changes in blood flow? And how do those changes in blood flow associate to the behavior of the animal or human? And that happens through an effect called neurovascular coupling. When a neuron or group of neurons fire, they use calcium and potassium ions, and all of these nutrients get used up and have to be replenished by the bloodstream. And that replenishment happens at a very small scale initially before kind of, propagating up the tree, if you will. But at that small scale, we can actually infer, okay, this small group of neurons, hundreds or maybe thousands of them, this small group of neurons must be active because it's using blood flow right now in a way that it wasn't before we asked the animal to do this particular thing.
Interesting. And what is that phenomenon called again? Because I think you kind of broke up there.
Oh, sorry about that. Yeah, so
Yeah.
the phenomenon is called neurovascular coupling.
Okay.
And it just relates actual neuronal firing activity to very localized blood flow that replenishes the neurons that are firing.
Okay, interesting. So we've talked a lot about the technology to augment limb functionality, right? So, but I think we need to kind of talk about the brain itself. So you did mention the motor cortex, right? So can we talk about how this actually affects locomotion and how this relates to what in your paper you guys called the PPC? So that's the posterior parietal cortex, right? So
Right.
how does this, I guess, these regions of the brain have to do with the work you're doing?
Yeah, so I did mention the motor cortex
Mhm.
earlier. That's one of the most commonly studied areas in BCI. Our lab, we are interested in the motor cortex, but we're also interested, as you mentioned, in the posterior parietal cortex. Now, these two brain areas live kind of in the same world, in the same stream. The motor cortex is more closely related to the actual limb movement. So specific areas of the motor cortex will control certain muscle synergies, like flexing my arm or grasping, a straw or something. But the posterior parietal cortex actually makes motor plans. It's a more cognitive area. It integrates vision and motor intention. So for example, it may not innervate flex my arm, but it will make the decision of, this glass is off to my right, my hand is slightly to the left of that glass, therefore I will need to move my hand to the right. And so it kind of takes into account reference frames between the thing you want to move, your goal, and your vision, and puts all of these pieces together. And that gets sent off to other parts of the brain for future planning and then also execution at the motor
Okay,
cortex level.
so goal-related neurovascular signals, right? Is that what we're talking about?
Goal-related neurovascular signals. Yep,
Okay, cool,
exactly.
cool, cool, cool.
So the reason that we were interested in goals specifically for functional ultrasound is when it comes to brain-machine interfacing, hemodynamics has a bit of an Achilles heel, and that's the hemodynamic delay. Between the time that the neurons start firing and the time that we can actually detect a change is on the order of about 1 second. And in that 1 second, the person may be kind of moving on or doing something different. That's a real latency
Wow,
that counts, right?
wow.
So if we were to just decode motor goals from the motor cortex instead, not goals, but actual actions, the actions might be too fast. On the other hand, if we go to posterior parietal cortex, where the goal remains consistent, that's a real key, because now we know if the intention was to move to the right using my hand, even if my hand is off moving and its velocity is changing, its position's changing, but one thing that's not changing is my goal. I still want to move my hand over to pick up the glass. And so that is a kind of more consistent, long-lasting signal that we can pick up more easily with the functional ultrasound.
Interesting. So what you're saying is the intention or intuition is actually in the PPC, right? But the actual locomotion is, I guess, controlled by the motor cortex.
Roughly speaking, yeah, that's
Okay.
right.
Okay.
The picture gets a little more complex when you
Mm.
really start digging, but for our purposes, yeah, I think that's the high level overview.
Interesting, interesting. So if you don't mind, can you walk us through the process of, I guess, setting up this experiment in the lab, right? So I guess you guys use animal models, right?
Yeah, that's right.
All
Before
right.
you can ever do these sorts of things in humans, you have to
Mhm.
prove that they work in animals.
All right.
And animals are our saviors in a lot of ways. MRI machines and a host of other medical miracles were all developed with animal models. So yeah, for this particular study, we use non-human primates. And the way that the study works is actually incredibly simple compared to what we usually do. So back in the day, when before we had Utah rays in humans and we had more of them in monkeys, that required surgery, just like the humans. But the greatest thing about functional ultrasound is that we don't have to remove the dura mater that protects the brain, and we don't have to penetrate the brain in any way. So we literally go in, we set the ultrasound right on top of the dura, and that's it. The setup is literally minutes long once you're ready to go, and that's it.
Interesting, interesting. So now the device is situated, right? So what sort of activities or I guess experiments are carried out to actually test these processes?
Yeah, so we want ultimately to tell, can we detect movement intention from the brain directly? Now, in humans, you can instruct them, tell them, think about a movement, imagine a movement. It's a little bit harder to tell a monkey that. Well, it's very easy to tell them that. They just won't do it, right?
They won't do it. Monkey see, monkey do. Yeah, so much for
Yeah,
that, right?
yeah. And so what we actually trained these monkeys to do was what are called memory delayed movements. So they would be given a cue on a screen. This is much like a video game. Something would pop up in their peripheral vision, maybe off to the right. But importantly, they would remain fixated on a small dot in the center of the screen. So they would keep their eyes centered, they would keep their hands centered using a joystick, and they would remember, I saw something off to my right. And then 5 seconds later or so, that little fixation dot in the center of the screen would disappear. And they would then have to, as quickly as possible, move to the remembered location. So they go, I remember there was a movement off to the right that I was being cued to do. Now I'm going to go and do it. And in that period, which was about 5 seconds long in our study, we knew that they know where they're going to go, but they're purposely not moving yet, right? And that's the key, because during that period, we can actually use signals from the brain to try to decode, predict they're going to move to the right or they're going to move to the left. They're going to move their hand versus their eye. Um, and if we can predict it, we know they haven't actually moved yet, that we're predicting their motor intention, not their execution, because they haven't actually done the movement yet. And that's the proof of concept that gives us the confidence to go and test this now in humans, to say, now we can, with some confidence, say that we'll be able to detect motor intentions in humans as well.
Interesting, interesting. So to decipher the information you guys get from these experiments, right? So I guess you guys make use of neural networks. So can you, now this is the field I do my research in as well, so artificial intelligence. Can you kind of brief us on how you guys are using AI, machine learning, to augment your work?
Yeah, so we've done a bunch of different approaches. In this particular paper, because we were using a brand new technique and this was a proof of concept, the last thing we wanted to do was give the impression that it was incredibly hard or you needed an incredibly advanced technique. So what we did was start with the kind of fundamental building block of linear techniques, and that's principal component analysis. So this is a linear technique that everyone understands in the field. In terms of decoding, it is, the vanilla approach. And so we took that, we modified it slightly. We used something called class-wise principal component analysis. And what that does is it estimates nonlinear interactions in a machine learning way, but using kind of just stacking multiple linear techniques together. So we compute the PCA, but we do it for all of the different classes separately. So we aggregate the data and the training data for when the monkey was going to move left versus right, and that's two separate PCAs that we perform. And then at the end, when we're doing the decoding, we actually decode twice, once in each subspace. Or if we have more classes, we decode 4 times or 8 times. And then we calculate backwards and use the Bayes probability to say which one of these actually has the best evidence, and we pick that solution. And so again, this is kind of approximating a nonlinear decode, but it isn't fundamentally a nonlinear decode. We have used neural networks as well, but again, in this paper, we tried to keep it as straightforward as we could while also being effective.
All right. So are you guys envisioning using these models in the pipeline, right, of these devices, or am I mistaken in thinking that?
So, I mean, the great thing about linear models is they're incredibly robust.
That's right.
So this will probably serve as our starting point for all future studies at this point, because we know that it works so well. It works across animals, it works across task types. We've now tested this in a number of different tasks that aren't published in the paper. And the approach is just really, really robust to all these things. At the same time, it's going to be limited in its ability to perform at its very, very peak level. So it will probably eventually serve as like an entry point to get you started, make sure that your decoder is working, debug the system, and then you'll probably move back to using whatever advanced neural network decoder you need for your particular application after that.
Interesting, interesting. So I guess the benefits of functional ultrasound is quite obvious, right? So another benefit, because you did mention the part of the brain called the dura mater, right?
Right.
Am I pronouncing it right?
Yeah,
All
I've
right,
heard it a couple different ways, so
all
you're as
right,
good as me.
all right. So I guess it's this part of the brain structure that is situated between the skull and the brain itself, the brain tissue.
That's right.
Now, with previous BMIs, there's actually damage to the dura mater, right? So can you explain to us why this is actually a problem?
Yeah, so people tend to think of the bone as being kind of the most scary thing, and maybe it is the most scary thing to remove
Mhm.
in terms of, if you're not a neurosurgeon. But what's actually scary, the one that actually introduces risk, is once you cut open the dura mater. Because now, once you open this protective membrane, you open the brain to risk for infection. And you could, as it sounds, it's very scary. If you have a brain infection or an abscess, these sorts of things can be very serious and life-threatening. So if you can maintain the dura, you can keep it there permanently, and you never actually insult it in any way. You just sit on top of it. This is a much, much safer approach overall. So even though you do have to remove the skull, that is a relatively low-risk procedure by comparison.
Interesting. And with functional ultrasound, that part of the brain is actually not disturbed at all, right? Not
Correct.
damaged.
Yes, we can image through the dura without any problem, and in fact, even fibrous tissue up to 4 or 5 millimeters thick, we don't seem to have much problem at all. Bone is still very difficult. The energy levels that are required to go through bone to actually penetrate through it using ultrasound waves is fairly high, because the signal attenuates and kind of dissipates as it
Dissipates, yeah.
goes through the
Mm,
bone.
mm.
And what that means is the amount of energy you have to deposit above the bone is quite high, and it
I
creates heat, and you don't
creates
want
heat.
to burn anyone, right?
Oh, okay. That makes sense.
So going through the bone does present a problem. That being said, not too long, or actually I think it might have come out right before our paper, our collaborators put out a paper where they used transcranial ultrasound, functional ultrasound, where they actually put the transducer above the transtemporal window. So this is just kind of right above your temples, right? This is the
Wow.
thinnest part of the human skull. And it's thin enough that with the right sequences, you can actually beam through this. And so
Wow.
there is hope for ways of getting through the brain, but we have to think
Wow.
very cleverly.
Wow. And we're talking about frequencies or wavelengths that are not deleterious to brain tissue, right?
Yeah, that's right.
Okay.
These are the same types of, this is the same wavelengths that you use on your unborn child that have been safe
Okay.
and effective for tens of years.
Okay. All right. Awesome. So now, what would you say the current limitations to functional ultrasound are? So, what's hindering us from actually making this technique more ubiquitous for people who actually need it?
Yeah, so this study, as I mentioned, is really the first step. It's a proof of concept, and there's a lot of steps to be done between now and something like a commercial product. The first problem is getting through the skull. Ideally, you would want to do this totally non-invasively, but the world isn't always ideal, so we're going to start minimally invasive. So that means you could either have a piece of skull removed and image just acutely, say in an operating room, or you could replace a small portion of the skull with something that's ultrasonically transparent, but structurally sound, feels just like skull to the person, but gives you a sort of window to the brain that's permanent, which would be a really exciting way of doing things. So that's one thing. The other thing is, and I mentioned this before a little bit, is the hemodynamic delay. So applications that require very low latency, very, very fast response are going to be hindered by the fact that blood flow is slower than the neuronal firing that is underneath its appearance. So that will limit the speed of these types of BMIs. So we have to think more about what types of applications are suitable for goal decoding or suitable for other types of cognitive or psychiatric states. We started with a motor BMI because that's what we specialize in, it's what we know, and it's a part of the brain that we understand really pretty well by comparison to others. But that doesn't necessarily mean it's the only type of BMI that exists and will exist. So finding the right applications is also key.
Interesting, interesting. So, what would you say, I guess, is the next step for you and your team now? So, what's next, right? So, there's this proof of concept. What's the next, I guess, chunk to go at this point?
So yeah, a couple of things. One, we're really excited about some of the science that's made possible about
Mm,
this. So we have a couple of ongoing studies looking at this area, the posterior-parietal cortex, now that people are becoming familiar with functional ultrasound and sort of trusting the types of signals it creates. It can it can image the brain with about 10 times the resolution of fMRI. So that opens up a whole host of possibilities of, with these super sensitive signals, what we can learn about how these parts of the brain function. So there's a very fundamental neuroscience side of the lab for sure. The other things that we're interested in are doing this in humans. So as I mentioned, we would really like to see all of our technology translate and make people's lives better if we can. And so we think that this is one technology that could. So we're pushing as fast and as hard as we can to get this working in human beings as well. And so that's really what's next on our radar.
wow, awesome, awesome. So, yeah, Dr. Norman, is there anything else you think we haven't touched on that had because
I
yeah,
think
this was awesome. This very informative to say the least.
yeah, it's a lot to cover. It's BCI in general is a very multidisciplinary field. You need some understanding of wave physics and
Mm.
ultrasound, and the medical field and neuroscience. And there's so much, and it's such an
Computer
exciting
science,
field.
obviously.
Lots of
Yeah,
computer science.
material science.
Yep,
Yeah.
materials.
Mm,
Yep, there's design, so that's some mechanical, a lot of electrical engineering around the electrophysiology happening underneath.
sure.
There's just so much to learn, and it's such an exciting field. And so if anyone's listening and this it all sounds exciting, I just encourage you to get involved. And because there's so many entry points to the field where you can make a big difference, and it's growing so quickly that I'm excited to see more people coming into the field.
Interesting, interesting. So I remember when we first started this interview, you actually did touch on this intersection between applied and fundamental science, right? So the science you're doing in labs right? Or that other researchers are doing like yourself, right? And the research that's being done in the private sector. So where do you think these two dynamics are starting to find synergy, and where do you think it could actually help the work that researchers like yourself are doing?
Oh yeah, this is an incredible kind of symbiosis that's happening where companies like Neuralink and Kernel that are, on the news for developing new types of hardware for brain imaging and recording, those techniques will find and are finding their ways into academic labs very fast.
Mm.
So things like what Neuralink is creating, these, hyper thin electrodes that can be sewn into the brain tissue with minimal damage. Um, they have onboards, what's called onboard spike sorting, something that to make a chip like that that has those sorts of capabilities is extremely expensive and prohibitively expensive for academics. So academics will come to benefit from what the private industry is creating. And the other direction is maybe even easier to see, that none of these companies would exist if the academic neuroscience hadn't been there to build a foundation, an understanding of how the brain works and encodes movement.
I
Uh,
was so hoping you would actually touch on that. I was praying. I'm like, God, please let him actually say that. Because yeah, I mean, we know the libertarian types. They'll latch onto something like, okay, the private sector is making it all happen, right? But let's not forget, most of this work is fundamentally being done by academics, right? So we need
that's
to
right.
give props where it's due for everyone
Yeah.
involved, really, right?
Yeah, academics, and don't forget the funding agencies. This is
Exactly.
decades of government funding that has made all of this possible through the National Institute of Health, the National Science Foundation. That's who makes all of this possible. So the taxpayers at some point have actually contributed to this effort. So everyone is a part of it.
Of
And
course.
without that involvement and that funding, none of it would have happened.
Of course. And yeah, I just love the fact that we're actually starting to touch on this right at the end of our interview, right? Because that's one of the reasons why I've embarked on this project with this podcast, right? Because I want people to know where their tax dollars are going, at least when it comes to science and research, right? So
That's right.
everyone has a part to play in progressing research and progressing fundamental science. So on that note, Dr. Norman, I can't really thank you enough. This has been super informative. And I hope to do this again whenever you guys drop a new paper. Please let me know, and we'll find time to set up another interview, right?
Absolutely. Yeah. Thank you for having me. It's been my pleasure.
Right. Awesome. Thank you.
Yep.